All right, everyone. Welcome to the kickoff lecture of our M42 RAG Framework Technical Deep Dive course. Before we jump straight into defining RAG, let's first walk through our full course outline so you'll all know exactly what we'll cover over the whole series and how each lesson builds on the last. Course outline segment. Let's go through every module one by one to set clear expectations for this training. First, what is RAG? Today's lecture. We'll unpack all core pain points of raw LLM applications, explain RAG's core business value, and break down the architecture and operating logic of production-grade industrial RAG. This is your foundational starting point. Second, Naive RAG will dissect the complete end-to-end workflow of basic vanilla RAG, weigh its strengths and obvious limitations, and lay the essential theoretical groundwork we'll rely on for all enhanced RAG chapters later. Third, tool ecosystem for building RAG. We'll list out all mainstream core tools across the entire RAG pipeline, then sort out the reasoning behind how we pick the M42 tech stack and supporting tool chains for enterprise use. Fourth, introduction to M42 framework. We'll talk through the original design intentions behind building the M42 framework, dissect its horizontally scalable architecture, and walk through every core component, plus how they coordinate and work together. Fifth, implement Naive RAG with M42. Hands-on demo time. We'll build a complete basic RAG system entirely on M42 step by step, covering everything from initial configuration all the way to final online deployment. Sixth, enhanced RAG workflow on M42. We'll break down M42's proprietary 6-stage enhanced RAG pipeline, analyze its service orchestration modes, and help you fully grasp the logic of complex industrial RAG systems. Seventh, deep dive into M42 component system, multiplied by. We'll take apart every core module inside M42 one by one, learn their interaction patterns, and unpack the underlying design principles that power the whole framework. Eighth, preprocessing algorithm deep dive. Master input text enhancement, query rewriting, and other front-end optimization techniques, so you can boost retrieval accuracy right at the data source stage. Ninth, Retriever deep dive will compare sparse retrieval, dense retrieval, and hybrid retrieval side by side, explore generative retrieval technology, and clarify key criteria for choosing the right retriever for different scenarios. 10. Retrieval strategy deep dive. Analyze adaptive retrieval, conversational retrieval, and agent-driven retrieval strategies, and cover targeted optimization methods for different business scenarios. 11. Alignment strategy deep dive. Focus on index optimization and retrieval enhancement solutions, and discuss how to resolve two big industry headaches: outdated knowledge and LLM hallucinations. 12. Compression and re-ranking deep dive. Learn context compression and result re-ranking technologies to lift final answer quality and strengthen the relevance between retrieved context and user queries. That's our full 12-lesson roadmap. We'll start with fundamentals today, move from simple basic RAG to complex enhanced industrial RAG, then dive deep into underlying algorithms, and wrap up with hands-on M42 practice and advanced optimization strategies. Everything builds sequentially, so don't skip any section if you want to fully master the framework. Now that you know the full learning path, let's dive into today's core topic: what exactly RAG is, and why raw LLMs can't cut it for enterprise production use. First off, let's talk about the 5 huge headaches raw LLMs bring to every enterprise tech team. Number 1 is knowledge cutoff. All LLMs are trained on fixed datasets that stop at a certain date. They can't access any new real-time information after that training window. If you ask about latest market reports, breaking industry news, or newly updated company policies, the model's totally out of touch. Second, terrible long context handling. You've all heard the phrase lost in the middle, right? When you feed a super long document into an LLM, the key details buried in the middle just get ignored completely. Plus, Processing massive text chunks burns through tons of compute tokens and jacks up your cost. Third, zero built-in domain expertise. Regular LLMs lack deep professional knowledge for vertical industries like medicine, law, engineering. Throw complex, non-standard industry docs at them, and they'll misinterpret critical specialized data every single time. Fourth, no way to access private internal data. Your company's confidential docs, intranet databases, internal meeting records, standard LLMs can't touch any of this private content. That creates a hard wall stopping AI from plugging into your daily business workflows and internal knowledge bases. But wait, there's an even bigger make or break risk that overshadows all four of those issues: hallucination. That's our fifth pain point. LLMs will confidently make up facts that sound totally reasonable, but are completely fake. In business scenarios, this leads to wrong, high-stakes decisions and destroys user trust in AI tools entirely. That's the biggest reason teams can't roll out raw LLMs to production. Okay, so we've covered all the LLM flaws. Now, let's introduce RAG, the solution built to fix every single one of these problems. RAG stands for Retrieval Augmented Generation, and it brings four core superpowers to the table. First, real-time knowledge access. RAG tears down the knowledge cutoff barrier. You can upload brand new documents, latest industry trends, updated internal policies anytime, and the system will pull that fresh info instantly for every user query. Your AI answers will always be up to date. Second, guaranteed factual accuracy. Every single response the model writes is grounded in your verified internal enterprise documents. This slashes hallucinations to nearly zero, so every output is reliable and traceable for business use. Third, smart text optimization. RAG automatically splits long, messy texts, filters out redundant fluff, and only feeds the most relevant snippets to the LLM. This boosts answer relevance while drastically cutting your token consumption and compute costs. Fourth, enterprise-grade security and domain adaptability. RAG supports fully private offline deployment, so all your sensitive data stays locked inside your intranet. It easily meets strict data compliance rules for regulated industries like finance and healthcare. Now let's walk through the basic end-to-end technical architecture of standard RAG, using the diagram we have on screen to make this crystal clear. I'll split the whole workflow into four simple stages. Stage 1. Offline document preprocessing and index construction. First, all your raw business files sit in the document store. A background service called the Documents Indexer job pulls these files, splits them into small, readable chunks, then sends those chunks to an embedding model. The embedding model turns plain text into numerical semantic vectors that machines can understand. Those vectors get saved permanently into VectorDB, while a separate metadata store logs all document index info and embedding configs. This whole process is offline work. We build the knowledge base once and reuse it for all future user questions. Stage 2. Vector storage layer. VectorDB's whole job is storing all those semantic vectors and powering fast similarity search. The metadata store keeps track of every document's index rules and embedding settings, so we can trace exactly where every retrieved text snippet comes from later. This layer is the brain of our knowledge library. Stage 3. Real-time query processing via query service. When a user types a question into the chatbot front end, the request hits the query service first. The service takes the user's query, runs it through the same embedding model to turn the question into a vector, then searches VectorDB to pull out the most semantically matching document chunks. It bundles those relevant chunks as context, then builds a complete structured prompt, combining the user's original question and retrieved context. Stage 4. LLM generation and user interaction. The finished prompt gets sent to our LLM model. This can be closed-source APIs like OpenAI or open-source self-hosted models like Llama and Falcon. The LLM only generates answers based strictly on the context we pulled from our internal docs, then sends the final accurate response back to the user through the chat front end. Every answer has clear source references, no made-up facts. Let's quickly clarify the difference between RAG and agent because people mix these two up all the time. Think of it this way. RAG is your dedicated knowledge retrieval layer. Its only job is fetching reliable external document facts. It acts like a static, trustworthy knowledge library for the AI. It's perfect for simple, one-turn Q&A where you just need to look up a single fact without complicated reasoning. An agent is the autonomous decision-making layer. Agents can plan multi-step tasks, call multiple tools, and chain together rounds of reasoning. It's the dynamic executor that figures out how to solve complex problems step by step. And when we pair them together, that's agentic RAG, the industrial standard. RAG feeds the agent stable, accurate external knowledge, and the agent can automatically run multiple rounds of RAG retrieval, cross-check info across dozens of documents, and handle complicated multi-step research tasks that plain basic RAG can't manage alone. Next, let's talk about resource consumption for industrial production-grade RAG systems. 3 distinct workloads that all need separate resource isolation to avoid performance crashes. First, model inference workloads. This is GPU-heavy. Running embedding models and LLMs demands massive parallel GPU compute. You have to lock down dedicated GPU resources, no shared preemption allowed, or your response latency will spike unpredictably. Second, vector retrieval workloads. This is memory and I/O intensive. Vector databases run constant high concurrency read and search operations. You need standalone memory and separate storage paths to stop I/O conflicts from slowing down your document search speed. Third, business logic workloads. This runs on CPU. All data preprocessing, workflow orchestration, and post-processing logic lives here. Deploy these on isolated CPU containers, so sudden GPU traffic spikes don't break your core business pipelines. Big takeaway here. If you want a highly available, high-concurrency industrial RAG system, you must split these 3 workloads onto separate physical or logical resources. Resource contention between them will tank your whole system's stability and speed. Now, let's cover the 2 mainstream ways teams build industrial RAG architectures, and then explain where our M42 framework fits in. Option 1. Cloud-native microservices architecture. This builds a full 3-layer foundation with gateways, service registries, and centralized config management. You split every component into tiny independent microservices that scale separately. It works great for consumer-facing products, with millions of documents and sky-high concurrent traffic. But the trade-off is massive operational overhead. You need a big engineering team that knows container orchestration inside out to maintain this complex stack. Option 2. Minimalist distributed architecture. This cuts out heavy gateways and registry centers, with direct API connections between core services. The network topology is super simple to deploy and run. It has near zero maintenance costs, perfect for small and medium enterprises, internal company knowledge bases, and lightweight apps with under 10,000 total documents. The only downside is it can't scale as far as full microservices for massive traffic. That's where our M42 framework shines. M42 blends the lightweight, low O&M philosophy of minimalist distributed architecture with fully pluggable modular components. You don't need to stand up a complicated cloud-native microservice stack, but you still get clean resource isolation and easy component management. It hits the sweet spot between simple operation and flexible industrial-grade capability. Let's wrap up today's lesson with a quick recap to lock in the key points. Raw LLMs suffer from knowledge cutoff, weak-long context, lack of domain skills, private data access limits, and the critical risk of hallucinations. RAG solves all these pain points by enabling real-time knowledge access, factual grounded answers, cost-efficient text processing, and secure private data deployment. We first walked through our full 12-lesson course outline, covering everything from basic RAG theory to hands-on M42 development and advanced algorithm optimization. Standard RAG runs on a 4-stage pipeline: offline document indexing, vector storage, real-time query retrieval, and LLM-grounded generation. RAG handles static fact lookup, while agents handle autonomous multi-step reasoning. Combining them creates powerful agentic RAG for complex enterprise tasks. Production RAG has 3 resource-heavy workloads: GPU for models, memory or I, or O4 vector search, CPU for business logic that require full resource isolation. There are 2 main industrial build paths: heavy microservices for large-scale consumer apps and lightweight distributed setups for small internal tools. Our M42 framework merges the best of both worlds, delivering modular, scalable RAG without heavy infrastructure maintenance work. That's all for our intro to RAG today. Next lecture, we'll dive deep into the full workflow of naive RAG, break down its pros and cons, and lay the theoretical groundwork for all the enhanced RAG upgrades we'll cover later in this course. Any questions before we move on?